Hello and very good morning. So today we will do the presentation and the title will be about power quality enhancement in a standalone PV system using active filter. And the first one will be project introduction. So good day everyone. Today I will briefly introduce my project. This project is about solar photovoltaic or PV system. So solar PV system converts sunlight into electrical energy. However, PV system, especially a standalone system, can face power quality problem. This problem include voltage fluctuation and harmony, mainly caused by inverter switching. To solve the issue, an active filter or APF is used. APF helps to reduce harmony and improve power quality in real time. Therefore, integrating APF in a standalone PV system ensures a more stable and reliable power supply.
For my part, methodology, the purpose of active pole filter is specifically designed to identify and extract harmonic component from a 3000-watt AC load. The system architecture is divided into four main stages to ensure precise signal processing. For the first point, input and conditioning. The 230 VRMS AC source is first processed through a resistive voltage divide R5 and R6. This stage is critical engineering choice to safely attenuate the high voltage to approximately 200 volt peak, protecting the operational amplifier from electrical stress. For the second point, the filtering and control. A second order of Salenki high pass filter isolates the harmonics, which are then used as feedback for a closed loop switching regulator operating at 10,000 kHz.
So for the calculation, the voltage input is 325.27 volt, which is too big because it is the power of sun needed to convert to electrical value because it is too big. So we need to use a lower voltage which is 200 volt. So to use the 200 volt, we need to readjust something which is we need to adjust the RA and RB. So RA we will use the 125 kilo ohm and RB we will put 200 kilo ohm. Number two is power load. So this part we will need to find the IRMS, and after the calculation we got around 13.08 ampere. And to find the R2 we will use the voltage Kirchhoff divider, which is V equal to IR, and after the calculation we get 17.63 ohm. And next we find the R1. So after the calculation we get the R1 is 100 kilo ohm, and the next one is voltage gain, and after the calculation we get 2. And for safety margin verification, which is design current, 13.04 will be multiplied by 1.25, which we will get 60.30 ampere. This margin ensures the robustness of power handling component against fluctuation in solar irradiance and load.
So for my part, I will explain simulation result and waveform analysis. So as you can see, we have three different of waveform, which is V in, new V in, and V out. So the V in is direct from the power of sunlight. So it is 325.27 volts. It's too big for our filter, so we drop using the voltage divider into 200 volt. So after the power field crossing after crossing the filter, the voltage out will be 50 volt. So the transit analysis performance using LT-SPICE confirm the successfully operation of the signal conditioning and filtering stage. This input voltage Vin was is started simulation waveform with a peak value of 325.27 27 volt, which was efficiently attuned to approximately 200 Vin new by the resistor voltage divider. The attenuation was a developed engineering decision to ensure the LN741 operationing amplifier operate safely, which is linear region thereby preventing saturation and minimizing high voltage stress. The filtering output voltage Vout had significantly reduced magnitude, demonstrating that the second order Salinki high pass filter successfully blocked the 50 Hz fundamental power component while insulating the high frequency harmonic contact. So the next part is summary of key result. So we have theoretically value and simulation value. So as you can see, the cutoff frequency is almost same. The percentage of error is 0.43%. Attenuated Vin is 0.01%. Load current is 0.07%. FSD current limit is verified. So this all.
Dan di sini anak perempuan farmasi. My matric number is 241364053. So for discussion part, I will explain how the simulation result confirms the operation of the design circuit. So based on the circuit design and the simulation result, the circuit function as a second order Salinki high pass active filter, which we use LM741 op-amp. From the AC frequency response, the output gain increase. We can see from the graph that I have attached there. Increase as the input frequency also increase. So this confirms the main characteristic of the high pass filter. So where the low frequency, like such as 50 Hz, are attenuated, it doesn't allow. While higher frequency components are allowed to pass through the system. So from the simulation waveform, we can see the output voltage become more stable at the higher frequency. This indicates that the filter reached its passband region and operates efficiently within the designed frequency range. So when we see that, when we do the calculation, referring to the design calculation, that the cutoff frequency was calculated by using normally used FC equals to 1 over 2 pi RC. So by using, we assume we substitute R equals to 100 kilo ohm, C equals to 16 nanofarad, and we calculate the frequency. Cutoff frequency is we get 99.47 Hertz. So when we do the simulation, we get the cutoff frequency is approximately 100 Hertz, which it gives a small percentage error, which only 0.53%, which validates the accuracy of the component selection and the circuit configuration. So when using the open LM71, it's provide better gain and a more stable response compared to a passive filter. We know we have a lot of disadvantage using the passive filter. So additionally, the input voltage is attenuate from 325.27 voltage peak to approximately 200.20 voltage peak using a resistive voltage divider. So from here we can see the deviation is about 0.01%, which is ensuring safe operation and control the circuit theory. So when overall, I can say the results confirm that design high pass active filter operates as expected and it is suitable for signal level harmonic extraction in the standalone PV system. That's it. My name is Aishwarya Desing and my metric number is 24136295. So let's continue from the discussion to the conclusion. In conclusion, this project successfully designed and simulated a high-pass active filter to enhance power quality in a 3000-watt standalone solar PV system. This means we focused on improving the quality of the electrical signals in a solar system, ensuring better performance and reliability. By isolating harmonic components with a precise 99.47 Hz cutoff frequency, the system effectively attenuates the 50 Hz fundamental power frequency to isolate higher order noise. In other words, the filter removes unwanted disturbance that could affect sensitive equipment and reduce system efficiency. Regarding system efficiency, the sensing circuit maintains an overall efficiency above 98% due to high impedance design. This shows that the system operates with minimal power loss, which is important for continuous operation in real world conditions. For the engineering safety, a 25% of safety margin ensures that the system can reliably handle peak currents up to 16.30 ampere during solar irradiance fluctuations. This gives confidence that the system will remain stable and safe even when solar output suddenly changes. Finally, let's look at the future scope. While providing a robust signal level foundation, future work will integrate power level switches and advanced closed loop strategies for practical industry application. This points to the potential for scaling the design to industrial level PV system with practical and real world implementations. That's all from us. Thank you very much. Thank you.